Okay, then we can get started. Yeah, so Mircea Sebe is going to tell us about nominal matching logic.
So my name is Mircea Sebe. I'm a PhD student at University of Illinois at Urbana-Champaign, and I'm here to talk to you about nominal matching logic with fixpoint. First of all, this fixed point binder, which is quite crucial to our current work. It's also the foundation of the K framework, for those of you who are familiar with the K framework. If not, I'll just mention that it's a framework for defining semantics of programming languages. And being the foundation of K, we can effectively express all of the semantics in matching logic, which is why it makes it appealing as a target for formalization. And it's also very simple and very general, allowing us to embed many other logics using verification in it. So to get a bit more familiar with matching logic, I want to talk about patterns, which are effectively the formulas in matching logic. We call them patterns because semantically they match a whole set of elements rather than just one element in the universe. So you can think of it kind of like a model logic, but one of the main advantages that this allows us of this approach, of this logic, is that it allows us to express both terms and propositions pretty much homogeneously at the same level. So for instance, you can have patterns such as this crazy one right here, which is f applied to an existential. And under the existential, we can have a term, which is successor of x, and then a predicate is even, that's applied to x. So semantically, when you want to talk about the truth value of a proposition like it's even, it's going to be true when it matches the whole universe of objects semantically or nothing. So in this case, if something is even, if x is even in this case, it will match the entire universe of objects, and the conjunction is interpreted as set intersection, and successor of x is interpreted as just a singleton object. So if we're looking at an x that is even, this is effectively going to be successor of that x intersected with the whole universe, which is still the successor of x. And then the semantics of existential is effectively we take all possible x's and we take the union of all of these sets. So it may be a bit confusing to think about this right now, but what this is going to match is effectively f1, f3, and f5 all the way to infinity, f of any odd number. A signature of matching logic theory consists of tuple S, evar, svar, and sigma, which is made up of sorts, element variables, set variables, and symbols. This is all we need to construct patterns. And once we fix this signature, we have the following grammar, which allows us to build patterns, which is on purpose chosen to be as minimal as possible. So you can have a small x, so we can have an element variable, which is always going to match a singleton element. We can have set variables named as such because they can match a set of elements. We can have a symbol in our signature applied to other patterns. Then we have implication and bottom, which allows us to do propositional reasoning. Existentials, which allows us to do first order reasoning, and then the mu operator, which is used for fixed point reasoning. So just to give you an idea of the power of matching logic, we can effectively embed all of these logics in matching logic. So that includes Hoare logic, reachability logic, first order logic. We think pretty much everything that you might be interested in. That's the power of matching logic. And this is where our current work fits into the picture. So the previous work that I mentioned, which is nominal logic and matching logic without the fixed points, that's from 2022 by Cheney and Fernandez. And our current work builds off of that. And it can all be expressed in matching logic. So matching logic also has a proof system, which I blur this out because I don't want to get into the weeds of it. It's effectively got a set of axioms for propositional logic reasoning, just what you would expect, 2 axioms for first order logic, 3 axioms for symbol application and propagating logical constructs to symbols, some 2 technical axioms. We don't worry about that for now. And then we have the fixed point axioms, which are quite important for the technique that we're going to be illustrating. So the H fragment of the proof system, that's sound and complete, whereas H mu is just sound. And I want to also mention applicative matching logic, which is a variant of matching logic that's more suited for mechanization. It's like matching logic stripped down to the bare essentials. It's just as expressive as regular matching logic. One of the main differences is that it lacks sorts and symbols, singularity and signature information. So all you have is this set of symbols, and you have a binary operator called application, and you can apply a symbol to anything. And this is how you build symbol application. I'm only mentioning this because this is what we use in the formalization, which makes things easier, but not knowing this might make reading it a bit hard to understand, so just to be aware. We effectively can bring back sorts into the picture by formalizing them as a theory in applicative matching logic. I also want to talk a bit about nominal logic, introduced by Pitts in 2003. It's a first-order logic like matching logic. It was mainly designed in order to reason about languages with binders. So it has built-in constructs like abstraction, which we denote by this square brackets notation. We have freshness, saying that a certain atom is fresh in a term. And then we have support of a term, which is the set of, effectively a set of free variables in that term. And it also provides an axiomatization of alpha equivalence. It has a built-in swap symbol, which is at the base of everything. And the semantics are based on nominal sets, which you can think of terms, you can think of them as terms with nameless representations, because we want to abstract away bound names. This is what the axiomatization of nominal logic looks like. I don't want to dwell too much on this. You can have a look at this in your own time, make sure it makes sense, but it effectively enforces the semantics that we want. I want to talk a bit about our previous work, which is about defining, combining nominal logic and matching logic before we worried about fixed points. So the main point of that work was to leverage the power of matching logic as a very general logic that's used to reason about programs, and nominal logic, which has all of these useful constructs for reasoning about binders. And there were two approaches that were proposed in that paper. We have nominal matching logic, which is an extension of matching logic with nominal constructs. And we have nominal logic in matching logic, where we define nominal logic just as a theory in matching logic without changing the base logic. And this is what we used in our current work. We didn't want to change the base logic. We want to try and do everything in raw matching logic without changing things too much. And the nominal logic axioms, as I mentioned, are also first order. So they translate somewhat naturally into matching logic with a few caveats that I'll describe later. As I mentioned before, a significant drawback of this previous work was that we didn't have any fixed point or inductive reasoning. So we couldn't prove, we could prove interesting things, but only by assuming induction principles as axioms. I want to talk a bit about induction principles in matching logic. So this was touched upon in a previous paper by Cheney and Roshu. Effectively, by having the fixed point operator in matching logic, this allows us to define any algebraic data type. So we don't need any additional machinery in our logic, in matching logic. We can just use the mu operator to define effectively any algebraic data type that's recursive. And a cool thing about this is that we can derive induction principles for it. And I'm going to show you quick examples involving natural numbers in a second. And yeah, we can do proofs by induction by using this technique. So all that we need is these two axioms, which tell us how we can manipulate the mu operator when we see it. One is called prefix point, and one is called Naster-Tarski, after the famous theorem that tells us that the fixed point does eventually converge if certain conditions are met. And here's what it looks like for natural numbers, just to give you a bit of intuition. So if you have a symbol nat that you want to stand for all of natural numbers, you can axiomatize this with just these three axioms. So you can say that nat is equal to mu x, the least fixed point of this operation. And on the right-hand side, you have successor of x and 0. And the intuitive way to think about what this fixed point operator is doing is to start off with an empty set, assume x, capital X is an empty set, and then plug it in, you get a certain set, and then you plug it in again, and you plug it in until you get to a fixed point. So in this case, what you end up with is 0 and successor of 0 and successor of 0, and you get all the natural numbers. And the other two axioms are there just to ensure injectivity. No successor of x is equal to 0, and successor is injective. And if we have this definition, we are able to prove this induction principle for natural numbers, which says that if P is a predicate, let's say P is some pattern that matches some elements that we want to be true for that predicate. That's the idiomatic way to do things in matching logic. If 0 satisfies this predicate or is in this predicate, and if the predicate is closed under successor, then all of natural numbers are going to be in our predicate. And now we're going to talk a bit about the current work, the current contribution, which is expressing nominal logic in matching logic with fixed points. Our goal is to bring inductive proofs to languages with binders and to make more rigorous the use of induction principles to reason about languages with binders. We want to be able to derive everything from first principles rather than just assume some structure and assume that we have this induction principle for it, which could have bugs. Now it's just a theorem. And then we can use those induction principles to prove useful facts about our language. And those facts, as we have shown in this work, can be formally proved inside a proof assistant, such as Metamath Zero. But the same technique would probably be generalized to other proof assistants. So this is, on the right-hand side, what the analog for the previous axiom that we saw earlier is in terms of lambda calculus. So exp is the sort of expressions, lambda expressions. And then we use, again, the fixed point operator to describe our algebraic data type. So we have variables. We have application. We want to say that this set is closed under application, and it's also closed under lambda abstraction. And here on the bottom is the induction principle, which we have proved. It's pretty much identical to the one for natural numbers. And this is what these two look like in code, if you are interested. This is a Metamath Zero code. So the no junk axiom, as we call it, is pretty much exactly what I described earlier. You can see that we have the mu operator, we have variables, lambda abstraction. And the lambda case is quite interesting because it uses internally, it has this LC lam, which is just a tag. And underneath, it has this abstraction object that comes from nominal logic. So we have to use, every time we want to define a sort of binding construct in our language, we have to use this abstraction that's coming from nominal logic, so that allows us to actually use the axioms of nominal logic to reason about it. And then this induction principle is the one we proved. It's relatively straightforward to prove this. I'm not going to go into the weeds of it. It's pretty much exactly what we had before, except for the fact that at the beginning we assume that exp pred, as we call it, the predicate over expressions, is an expression, and which is why at the end we have equality rather than just implication. But otherwise, it's exactly what you would expect it to be. This is another real example of what our nominal theory looks like in matching logic for lambda calculus. I know it's a huge wall of text. I don't expect you to understand what's here. This is just to give you an idea of what it looks like. So the idea is that we, for each of the constructs, for each of the build the constructors of lambda calculus. We define it as a symbol in matching logic. We have an axiom that gives it its arity. As I mentioned before, we work in applicative matching logic, so we need to do this. And then we have another axiom for equivariance. And I will talk a bit more about this later. And this is one of the main theorems that we proved, that we used the induction principle for. And this is common identity about substitution in lambda calculus. I know it looks like, again, a bit of a wall of text, but if you actually sit down to look at this, what it's effectively saying is that if we are given two different atoms, A and B, and lambda terms P, P1, and P2 with A fresh in P2, we can prove this common identity about substitution. It's just pushing a substitution in through another substitution. And this was entirely proved out of the axioms of matching logic and the axiom that we saw earlier with a mu, with a least fixed point binder. Now we're going to talk a bit about formalization. I have no idea how much time I have left, but anyway, I'm going to try to be quick. So we chose Metamath Zero for a number of reasons. First of all, Metamath Zero is a relatively new proof assistant. It was developed by Mario Carnero as an alternative to Metamath. It's got an extremely small trust base, which is why it was quite attractive to us to begin with. Probably the smallest. Maybe the other contender would be Metamath, but even then it's smaller than Metamath in certain implementations. It's got native support for notations, unlike Metamath. It's faster than Metamath. It's got modern tooling, so it was quite nice to work with. And also we chose this because we had some expertise in the team already. We had a library that was already developed for matching logic in Metamath Zero priorly for another project. So we wanted to see how far we can take this formalization. I'm going to talk a bit about the main challenges of these formalizations and design decisions. One of the main challenges was working with a new proof assistant, which takes a bit of time to learn, but once you get used to it, it's not horribly hard, and I want to thank Mario for his support in getting familiar with the syntax and everything. Another technical challenge was figuring out exactly what we want the induction principle for lambda calculus to look like. If you look at the earlier paper, and also if you look at the formalization of nominal logic in Nominal Isabel, you will see that the induction principle for lambda calculus is a little bit different. One of the key differences, and this is what we started off trying to implement, but we ran into some issues. So the difference is in this requirement here in the third antecedent of the induction principle. So this is effectively saying that for the lambda case, we only have to prove the lambda case for certain, for only some atoms, not all atoms, which makes it easier for the user to use this induction principle, but makes it very hard for us to actually prove it. We tried to prove it. We ran into a lot of issues, so we figured out a different approach to do this. And the different approach is we dropped this requirement. We used the standard induction principle that comes from, that's exactly as we did for natural numbers. And then we use that instead. And we don't really need to worry about this. It's effectively a shorthand. It's effectively something to make the life of the user easier, but the user doesn't necessarily need it. And a lot of the times we found that it doesn't really add much. Another important decision that we had to make when designing this formalization was with respect to equivariance axioms. So for those of you familiar with matching with nominal logic, in nominal logic, do I still have time? All right. In nominal logic, every single symbol is equivariant in the sense that if you have a swap operation, swap of AB applied to a symbol and some arguments, the swap symbol is propagated to the arguments. And that is just one axiom in nominal logic. But for this formalization, we decided that instead of having this one axiom for every single symbol, we have a separate axiom for each symbol that we want to introduce. And that's to make it compatible with other theories. Maybe you want to have theories where you don't want to have equivariance for your symbol. So we don't want to force everyone using our theory to have every single symbol be equivariant. So whenever we add a symbol, we also add an axiom that says that the swap operation can be propagated through the symbol. We have one for variables. We have one for lambda abstractions. And if you look at the last line of these snippets of code, you can see that there's nothing particularly interesting going on. But we need these axioms. Another important caveat that I touched on during the presentation is that when you're working in a matching logic setting, as I said, patterns are multi-valued in the semantics, whereas in nominal logic, in an axiom, every single occurrence of a variable is a singleton. So if you naively translate the nominal logic axioms into matching logic without thinking really hard about whether something can be multi-valued or not, you run into problems that are caused by inconsistencies. So your axiom can just can be unsound because of that. So we have to make sure that in axioms such as A1, some variables are element variables, which forces them to be singletons, and some variables are meta variables. So just any pattern, so they can actually be multi-valued. So this is, in a way, another part of our contribution. It's trying to rewrite these nominal logic axioms in a way that's faithful to the original. It's idiomatic to matching logic, so as to allow as many things to be multivalued as possible, but also correct with respect to nominal logic. Right. And then another important challenge in the formalization was restricting the axiom F4, which you might know as the axiom that says you can always find a fresh atom for a set of atoms. In nominal logic, we force this set to be finite so that we can always find a new atom that's different from what's already in the set. But here, it's quite hard in matching logic to say that something is finite. You have to define natural numbers. You have to do all kinds of things to express finiteness. So instead, what we decided to do, and that turned out to be good enough, is to force this set for which we want to find a fresh atom. We want to restrict it to a singleton, to effectively just one atom, or a finite set of atoms that we can build by using a certain special operator that we added specifically for this purpose. I mean, this is a very technical thing. I don't want to bore you too much with this, but the main point I want to make is that things often don't go exactly as you plan when you have to actually sit down and formalize something in a proof assistant. And I want to talk a bit about the future work. As I mentioned before, this is a proof of concept of our approach. We want to prove a bit more facts about lambda calculus, more interesting theorems. We want to adapt this technique to other, hopefully more complex languages. We don't expect there will be any major blocker. We just didn't get around to do this for this paper. We want to find a way to simplify the proofs, streamline them, and maybe develop some meta theorems, some programs that allow us to build these proofs easier. Because this is a new proof assistant, and I was effectively working alone, a lot of things took a lot of time, a lot of very simple things, but we hope that we can make things much more streamlined in the future. And we want to make also prove that this embedding of the nominal logic axioms that we chose is faithful to the original semantics of nominal logic. At the moment, for our current work, we just translated them as best as we could and as it made sense to us for this work. So yeah, that's pretty much it. If you have any questions, I would be happy to take any questions. How did I do with time? All good? Thank you.
Any questions? So I have a question. You mentioned that one of your main theorems here was the substitution theorem for lambda calculus, right?
Yeah.
Do you know, I guess one of the selling points of like nominal logic is that, it allows you to prove the substitution stuff only once, and then you can, sort of instantiate it into anything that has binders or whatever. So can you do something similar here? Do you know whether it's possible to abstract this into a version which would save you the time?
Yeah. So that's the main idea. This technique can be generalized to any language. Probably not this exact theorem, because this exact theorem uses constructors specific to lambda calculus. But any extension to lambda calculus can also use this theorem. And if you want to have another language, yeah, I think this should generalize quite easily. That's the idea.
So you mentioned that you have to be careful in the way you state the axioms in order to not reach inconsistency. But I didn't get, how do you make sure that you don't reach inconsistency?
Yeah, so for, oops, sorry. For this, we don't really have a way to make sure about that. I mean, we have a pen and paper proof that's still a work in progress, and it's looking quite good, but we haven't published that yet. And looking at it, we also made sure we also used our expertise to make sure that things make sense, but the actual formal proof is still in progress right now.
Okay, so let's thank the speaker.
Thank you.